Picture this. You are in the final round of a technical interview. The problem in front of you looks incredibly simple. You write up a quick, elegant solution using strings, the most basic data type imaginable. The logic is flawless. But then the interviewer runs your code and bam, it times out. Why? Well, because Java strings have hidden costs that will absolutely slow down your code, and if you aren't careful, they will secretly tank your interview.
Welcome to The Explainer. I am so glad you're here today because we are going to expose these hidden Java string traps. Our mission is simple. We want to help you write faster, highly optimized code and arm you with the precise knowledge you need to completely ace your next technical interview. We're taking our source material and breaking it all down so you can see exactly where things go wrong and, more importantly, exactly how to fix them.
Okay, here is our roadmap for today. We're going to hit 4 main topics. First, the concatenation trap. Second, fast character frequency arrays. Third, sorting and comparing strings. And finally, avoiding substring overhead. Let's just jump right in.
Section 1, the concatenation trap, building strings in loops. So to really get why this is a trap, we first have to talk about immutability. In Java, string objects simply cannot be changed once they are created. This means that every single time you modify a string, like, say, adding a single new character to the end of it, Java isn't just updating that existing string. No, it's secretly doing a ton of work in the background. It's creating a brand new object in memory and copying all the old data over. Let's ground this. To truly grasp the cost here, let's look at a real-world example question you might actually face. Say an interviewer asks you, how would you append 10,000 user inputs into a single string log without crashing your program's performance? If you just use the standard plus sign operator to add those strings together inside a loop, your program is going to create 10,000 brand new string objects, copying increasingly massive amounts of text every single time. It's a massive bottleneck. When we compare the methods, the exact cost and the solution becomes super clear. Using string plus string inside a loop scales at an O of n squared time complexity. It gets exponentially slower as your data grows. But for performance-critical code, your escape hatch is StringBuilder. When you use the append method, it modifies the sequence directly without spinning up a new object every time. This brings your time complexity down to an amortized O of 1. It completely solves that real-world performance crash.
Section 2, frequency arrays, fast character math.
Now, the real secret sauce here is character math. If you grab a character in Java, you can actually do math with it. By simply subtracting the character A from any lowercase character, you perfectly map those letters to an integer index right from 0 to 25. So A minus A is 0, B minus A is 1, all the way up to 25 for Z. It is incredibly neat.
Let's lock this concept in with another real-world example question. If an interviewer asks you to track the most frequent letter in a massive document, how do you do it efficiently? Now, the instinct for a lot of people is to reach for a heavy data structure, like a hash map, to store those counts. But hash maps have overhead, right? They need more memory and more processing power to manage the keys and values. But with that character math trick we just learned, we don't need a hash map at all. Implementing this efficiently comes down to 3 basic steps. First, you just create a simple integer array of size 26. That's 1 slot for every letter of the alphabet. Second, you loop through your string by converting it to a character array. Third, and this is where the magic happens, for every character, you increment its count directly in the array using our math trick. Freak at index C minus A++. It is blindingly fast, incredibly memory efficient, and interviewers absolutely love seeing it.
Section 3, sorting and comparing, avoiding fatal mistakes. Because strings are immutable, you can't just sort a string directly in Java. You actually have to transform it. This is a clean 3-step process. Step 1, you extract the characters into an array. Step 2, you use Java's built-in arrays.sort method on that character array. And step 3, you pass that newly sorted array back into the constructor to create your new string. It's a fundamental pattern you absolutely need to have memorized. But what happens after you sort them? Here's our real-world example question for this one. You're asked to check if 2 sorted user passwords match perfectly. It's a high-pressure situation, you're typing fast. Do you use the double equal sign operator, or do you type out the full dot equals method? Well, if you want with double equals, your test cases might completely fail. And here's why. The double equals operator in Java compares memory references. Basically, it's asking, are these 2 variables pointing to the exact same physical object in the computer's memory? But dot equals compares the actual content. It asks, Do these two different strings contain the exact same letters in the exact same order? Always, always use .equals for string content matching in Java.
Section 4. Substring overhead. The O of N memory trap.
The substring method is honestly super convenient for pulling a piece of text out of a larger string, but it comes with some heavy overhead. Remember mutability? Because strings can't be changed, extracting a substring forces Java to allocate new memory and copy those characters into an entirely new string object. That single operation runs at an O of N time complexity. Let's test this with our final real-world example question. How do you parse through a 1,000,000-character string, constantly checking different segments of it without calling substring and timing out your algorithm? If you use substring inside a loop on 1,000,000 characters, you are churning out massive new string objects over and over again. Your system is just going to grind to a halt. The pro move here is to use index tracking. Instead of creating new objects, you just maintain integer variables, usually called start and end pointers. You literally just slide these pointers back and forth along the original string to keep track of the section you're currently analyzing. You are using a few bytes of memory for integers instead of megabytes for duplicated strings. It saves memory, it saves time, and it is the exact type of optimization that passes those brutal, hard interview questions.
Section 5. Ace the interview. Deep language mastery.
There is a fantastic quote from our source material today that I want to highlight. These Java-specific tips separate candidates who know the language from those who just know algorithms. This is such a powerful insight. Honestly, anyone can memorize an algorithm, but knowing that StringBuilder prevents O of N squared memory bloat, or that character math replaces a heavy hash map, or that substring creation drags down your parsing speed, that proves you actually understand the tool you are using to build the software. Algorithms might get you in the door, but it's this level of deep language mastery that ultimately gets you the job. So I want to leave you with this final provocative thought. The next time you sit down to solve a problem, look closely at your strings. What hidden costs are currently lurking in your code? Thank you so much for joining me for this explainer. I hope these breakdowns help you write incredibly fast Java. Keep learning, and I'll catch you next time.